Fundamentals Part 2. My name is Kate Gregory, and I'm continuing my introduction to C++, the most popular general-purpose programming language in the world. In this module, I want to cover something that every C++ developer simply must understand: exceptions. They're a great way to handle errors and problems, but because they disrupt the flow of control, they can mess with your manual memory management. I guess it's a good thing you aren't doing any, right? I'll show you how to catch them and throw them, and why letting locally scoped objects manage lifetime is even more important when exceptions are in play. As developers, we know that when a line of code executes, it might not work. You can count on errors and failures occurring throughout your application. In fact, a large part of programming is reacting to that. But some of them are more predictable than others. If you ask users for values, you have to assume at some point every single user is going to mess you up. They're going to leave something blank that they're not supposed to leave blank. They're going to enter a letter where they're supposed to enter a number, those sorts of things. There may also be kind of predictable business logic problems. So I'm trying to take $100 out of a bank account that only has $50 in it, and I don't have overdraft privileges on that account. Those kinds of errors you can test for, you can predict them. A good developer thinks of as many of them as possible. There are other kinds of errors that are much less predictable, and it's arguable that testing for them constantly would put a performance hit on your application. So every time you allocate another piece of memory from the free store, should you check and see if you actually got memory from the free store? You know, the vast majority of the time you're not out of memory. When you make a calculation that is supposed to fit in an integer, should you always make sure that you didn't have an overflow? If you put up a file dialog in a Windows application and let somebody browse to a file and then you go to open it, should you first check to make sure it still exists? They just browse to it using the operating system. When somebody has been running an application for a day or two and has authenticated to the application, should you continue to check to make sure they're allowed to read and write the files that they're reading and writing? Because, hey, their password might have expired while they were running the app. Most of the time, checking these sorts of errors every single time is an actively bad thing to do. I mean, checking error results takes time. You're going to slow your application down. And these things are really unusual, really kind of unexpected. And so that leads us to a best practice that says different kinds of errors should be handled different ways. Exceptions are not the only way you handle errors. Especially for expected errors, the best thing to do is to just test for them. If the amount to be withdrawn is greater than the amount available for withdrawing, do something, deal with it, put up an error message, tell the user what they've done wrong. Write exactly where you find the problem. That's when you have the most information. But the problem is that in some designs, some architectures, the code that actually finds the problem is a really long way away from anywhere that it can tell the user about the problem, or in some other way recover. So if you're in the user interface and you've just popped up a dialog and you've let somebody choose a file and then you test to see if the file still exists and it doesn't, you can just pop up a message box that says, hey, that file seems to have disappeared in the last 5 seconds. Please choose another one. But if you let the user choose a file and you take that file name and you pass it along to some member function of some business object who passes it along to someone else, who passes along to someone else, 6, 7, 8 calls down, then they go and open the file, they don't have a really good way to communicate directly to the user. So one thing you can do is have that chain of functions return true or false to indicate if there is a problem, for example. And then all the functions along the way in the chain, they need to test that return value. So if deeply nested function, carry on and do more things, else Well, I'll return false also. And then whoever called me will have to check me to see if I returned false, and so on, all the way up the chain. Couple problems with this approach. Some functions we're maybe going to just return void, nothing. So that's fine. You can toss on a return value to them. But what about functions like square root or find employee that are supposed to already have return values? Sometimes people will use signal values. So for example, if find employee returns an employee number, return -1 to indicate there was a problem. Or for square root, you could also return -1 because it has to be positive. Of course, this doesn't work very well with functions that could return a wide value of numbers or strings, all of which are perfectly fine and legitimate values. These signal values aren't always available to you. And if you get into trouble in a constructor, you don't have ability to return anything. Constructors cannot return. Some people get around that by saying, oh, you know what, I won't ever have my constructor do anything. I'll write this function called init, and it can return true or false, and then I'll always know if there was a problem. That really gives up most of the benefit of constructors for not much gain. Other people will set a member variable in the constructor when it succeeds to say that the object is valid, and then have all their other functions test the valid flag. Boy, that's really awkward. And of course, you open yourself up to people forgetting. They can forget to check that member variable to indicate whether the object is valid or not. They can forget to check the return value from the function. That's a problem. If your error handling relies on other developers remembering to do something, what are you going to do inevitably when they forget to do something? And the more infrequent the errors are, the more likely the forgetting is to happen. So if you think about users leaving things blank, that's going to happen constantly. Developers will remember to check for invalid values on a form. But having your network connection drop in the middle of a process, that's a lot rarer. It may never happen to the developer, and they may never think to test for it. So it's more likely for these unusual errors that people will not be checking return values or in other ways preparing to deal with those unusual situations. This is the real strength of exceptions. With exceptions, you can write your code a lot cleaner with no checking of intermediate return values along the way between a place that can deal with a problem and a place where it might happen. When this very bad, unexpected thing happens, we say the exception is thrown. And at that point, your flow of control, instead of going from statement to statement, jumps from the place where you throw the exception to the place that can handle it. And all of the code in between is skipped. That's the rest of the function you're in. And then when you go back to where that was called, the rest of that function. And when you go back to where that was called, the rest of that function. And so on, all the way. It's all skipped. Nothing else is run. A developer cannot forget to check this because there's no returning. It's a pretty serious behavior, and you save it for situations where you can't deal with the problem right where it happens. It's still the number one rule: deal with things as close to the problem as you possibly can. If you can deal with it right where you are, you have an if. If it's one or two functions away, maybe you'll still have return values and you'll remember to check them. But the further apart they get, the more annoying that chain of return value checking becomes, and the rarer the problem becomes, the more expense you're doing constantly if that has a computational expense. Just write it the straight ahead way and have the exception bring you back. Now, if you have an exception thrown deep within the business layer, you're not going to be able to say much intelligent in the user interface layer except there was a problem, please try again. So deal with it as close to the source as you can, because that's when you have the most information. I want to start by showing you how this works with a very simple example. We're going to come back afterwards, and I need to talk about something called stack unwinding. It's a very important aspect of exceptions, but we'll start simpler with basic throwing and catching. I have a small application here. There's just really 4 lines of code, and it's going to get itself into trouble. I'm setting up a vector of integers. We talked about vectors in the standard library module of this course, and push one integer onto it, the number 1. So there's only one element in my vector. Then I'm going to try to access a specific element. The at method, a lot like the square brackets, takes you to a particular element of the vector. There is no element number 99 because I've only pushed one integer onto my vector. So you can expect that this is going to cause me trouble. I'm breaking my own best practice of dealing with problems as close to the source as possible so that you can see exceptions without my having to construct a super complicated chain of function calls. It will get a little more complicated as the demos go on. I'm going to run this application. You can see I have a breakpoint here. And we'll just step over a line at a time. So that declares the vector, that puts the number 1 into the first element of the vector, and I'm going to try to access element number 99. And an exception has been thrown. And this is an unhandled exception because I'm not catching it. I'll show you how to catch them shortly, but when you don't catch them at all, they end up being shown to the user. So this says unhandled exception at memory location in executable name. And then this is really important right here. Standard, that's the namespace, out of range, at memory location, whatever. I don't care about that. It's telling me the type of the exception that's been thrown. And because it's a well-named class, I can just read that, out of range. In fact, because the standard library is all done as headers, I can even see here the comments and words and so on to help me understand what's going on. Now, your exceptions are not always thrown by code that you have immediate access to, the way that we have access to the headers of the standard library. And as well, I'm reading this message with my eyes, invalid vector subscript, but there's no way my code is able to react and do something intelligent. In order for my code to be able to react, at least even to just construct a nicer error message for my end user, I need to catch the exception. So I'm going to stop debugging. And come back here. And I'm going to wrap my code in a try. And follow it with a catch. Now, when you catch an exception, you need to say what it is that you are catching. And for now, and I'll explain this in more detail shortly, I'm going to catch this exception reference E. I don't have a lot of options about what to do with it, but I will print out its message. Let me just neaten up these lines. In the more general case, this might be a chain of function calls that would go a long way down. All the way down in that chain, whenever the exception is thrown, none of those functions return. All of them will come back and transfer control to a catch statement. Now, it has to be the appropriate catch statement, and I'll cover that in more detail shortly. I just don't want you to think that any catch statement will do. I'm going to put a breakpoint here now and run the application. I'll just let it run. And you can see that we end up here in the catch block. And I can hover over this exception E and see that same message, invalid vector subscript. I can also let this print out onto the screen. You can see the message is there also. At that point, if this application did something real, I would have to react in some way. But all I know is that something went wrong. I caught just an exception. when we got that message in the debugger, it was an out of range exception, and that's really a better choice to catch. Really, the only way to learn the names of these exceptions is to see them being thrown, that's the number one way, or to read the documentation, which I know is a little on the scary side. You can, in the case of vector, literally read its code, probably not what you want to do. If I come all the way up to the top, you notice that this includes standard exception. I can right-click here and say open this document, and in here I can see exception classes being defined. This is reasonably difficult to read, but the out-of-range exception is here, and that's how you could, for example, check the spelling of it. For most people, they learn what to catch either by having it thrown on them or by reading the documentation and understanding from the documentation what exceptions are likely to be thrown. I'm going to put breakpoints in both of these and run the application again. And just to tell them apart, let's put more information in here. So that when I catch the out of range exception, I print out a more detailed message. So we'll run it. We end up in this catch. If I take a look at E, I can again see that message, invalid vector subscript. And if I step over the line, my message prints out on the screen. If I continue to just step, notice we do not stop here and catch this. It's a really important piece of information. A try block can have any number of catches after it, and basically the exception is offered to each block in turn. The first catch block that catches what's been thrown gets it. All the others get skipped. To show this, I'm going to flip the order of my two blocks. So when I only caught an exception, out of range inherits from the exception class, so it was caught. When I caught both an out of range and an exception in that order, the out of range block caught it. Now, if I put breakpoints in both of these and run it, we're in the first catch block that catches the more general exception and prints out the more general message, and we don't go into the second one. So it's very important, let me just put these back in the right order, very important to catch the most specific exception first when you're using an exception hierarchy, and you should be using an exception hierarchy, and I'll talk more about